Hello learners, welcome to the course Statistical Methods for Economics, Bivariate Random Variable Continuous. In this session, we will discuss the concepts related to understand and define two-dimensional continuous random variable, specify the joint density function of two continuous random variables, obtain the distribution function for two-dimensional continuous random variable, solve various practical problems on bivariate continuous random variable. Importance of a bivariate random variable in economics. In the previous module, we have understood the concept of a bivariate random variable. What is the probability mass function of a bivariate random variable, its distribution function, and then solved some problems on these concepts. Finally, tried to understand the application of the bivariate distribution in various domains of economics. Concept of bivariate continuous random variable. The study of bivariate continuous random variables involves two related random variables that can take on a continuous range of possible values. This means that both variables can take on any value within a given range, which may be finite or infinite, but it is still countable. In summary, bivariate continuous random variables are a statistical tools used to analyze two interrelated variables within a given sample space. For instance, if we want to study the income and expenses of the individuals within a certain organization, we must understand the mathematical concept of two random variables. Another example of continuous bivariate random variables include the height and weight of individuals or the temperature and humidity of a given region. In these cases, the probability of a particular combination of values for the two variables can be calculated using a joint probability density function. Understanding the behavior of continuous bivariate random variables is important in many fields including economics, engineering, and science. By analyzing the relationship between two variables, researcher can gain insights into cause and effect relationships, develop predictive models, and make informed decisions based on empirical data. Now, we shall see how a bivariate continuous probability density function is defined. Let x and y be two continuous random variables, and if S is the two-dimensional support of x and y, then the function f of x, y is a joint probability density function PDF if it satisfies the following conditions. First condition is that f of x, y is greater than or equal to 0 for all x and y. Second condition is that integral over x, integral over y, f of x, y dy dx is equal to 1. Third condition is that probability of A is equal to probability of x, y in A is equal to double integral over A f of x, y dx dy, where x, y in A is an event in the xy plane. Next, we shall understand the cumulative distribution function of a bivariate random variable. The bivariate cumulative distribution of x and y, if f of x, y is equal to probability of x less than or equal to x, y less than or equal to y for all x, y. That is, f of x, y is equal to integral minus infinity to y integral minus infinity to x f of x comma t ds dt. The following are some important properties of a bivariate CDF. From the CDF, the PDF of a two-dimensional random variable can be obtained as f of x comma y is equal to dou square by dou x into dou y f of x comma y. F of x comma y is a non-decreasing in both x and y. Limit as x tending to minus infinity f of x comma y is equal to limit as y tending to minus infinity f of x comma y is equal to 0. Limit as x tending to infinity f of x comma y is equal to f of y which is equal to probability of y less than or equal to y. Limit as y tending to infinity f of x comma y is equal to f of x which is equal to probability of x less than or equal to x. Limit as x tending to infinity f of x comma y is equal to limit as y tending to infinity f of x comma y is equal to 1. F of x comma y is both continuous from the right in both x and y. Problems on bivariate continuous distribution. Let f of x comma y is equal to cxy in the range 0 less than x less than 4, 1 less than y less than 5 and 0 otherwise be the joint probability density function of x and y. Find the constant c and probability of 1 less than x less than 2, 2 less than y less than 3. Consider the given function f of x comma y is equal to cxy in the range 0 less than x less than 4, 1 less than y less than 5 and 0 otherwise. As it is a joint density function, according to the condition of probability mass function, we have integral 1 to 5, integral 0 to 4 cxy dx dy is equal to 1, which implies c into integral 1 to 5 y dy into integral 0 to 4 x dx is equal to 1, which implies c into y square by 2 in the limits 1 to 5 into x square by 2 in the limits 0 to 4 is equal to 1, which implies c into 24 by 2 into 16 by 2 is equal to 1, which implies c into 12 into 8 is equal to 1, which implies c is equal to 1 by 96. Now, we compute probability of 1 less than x less than 2, 2 less than y less than 3, which is equal to integral 1 to 2 integral 2 to 3 1 by 96 xy dx dy, which is equal to 1 by 96 into integral 1 to 2 x dx into integral 2 to 3 y dy, which is equal to 1 by 96 into x square by 2 in the limits 1 to 2 into y square by 2 in the limits 2 to 3, which is equal to 1 by 96 into 3 by 2 into 5 by 2. Therefore, probability of 1 less than x less than 2, 2 less than y less than 3 is equal to 5 by 128. Suppose f of x comma y is equal to 1 minus e to the power of minus x minus e to the power of minus y plus e to the power of minus x plus y in the range x is greater than or equal to 0, y is greater than or equal to 0 and 0 otherwise is a distribution function, then obtain the probability density function. The joint probability density function from the distribution function is given by f of x comma y is equal to dou square by dou x into dou y f of x comma y, which is equal to dou square by dou x dou y 1 minus e to the power of minus x minus e to the power of minus y plus e to the power of minus x plus y, which is equal to dou by dou x into dou by dou y of 1 minus e to the power of minus x minus e to the power of minus y plus e to the power of minus x plus y, which is equal to dou by dou x of 0 plus 0 plus e to the power of minus y minus e to the power of minus x into e to the power of minus y, which is equal to 0 plus 0 plus 0 plus e to the power of minus x into e to the power of minus y, which is equal to e to the power of minus x plus y. Therefore, the probability density function is f of x comma y is equal to e to the power of minus x plus y in the range x is greater than or equal to 0, y is greater than or equal to 0 and 0 otherwise. The joint PDF of x1 and x2 is given by f of x1 x2 is equal to 4x1 x2 in the range 0 less than x1 less than 1 and 0 less than x2 less than 1 and 0 otherwise. Find probability of 0 less than x1 less than 1 by 2, 1 by 4 less than x2 less than 1. Consider the given joint probability density function f of x1 comma x2 is equal to 4x1 x2 in the range 0 less than x1 less than 1 and 0 less than x2 less than 1 and 0 otherwise. Now, probability of 0 less than x1 less than 1 by 2, 1 by 4 less than x2 less than 1 is equal to integral 0 to 1 by 2 integral 1 by 4 to 1 f of x1 comma x2 dx1 dx2, which is equal to integral 0 to 1 by 2 integral 1 by 4 to 1 4x1 x2 dx1 dx2, which is equal to 4 into integral 0 to 1 by 2 x1 dx1 into integral 1 by 4 to 1 x2 dx2, which is equal to 4 into x1 square by 2 in the limits 0 to 1 by 2 into x square by 2 in the limits 1 by 4 to 1. On simplification, we have 1 by 4 into 1 minus 1 by 16, which is equal to 15 by 64. Therefore, probability of 0 less than x1 less than 1 by 2, 1 by 4 less than x2 less than 1 is equal to 15 by 64. If x and y are two random variables having joint density function f of x comma y is equal to 1 by 8 into 6 minus x minus y in the range 0 less than or equal to x less than 2, 2 less than or equal to y less than 4, 0 otherwise. Find probability of x less than 1 and y less than 3. Also, probability of x plus y is less than 3. Using the given joint probability density function, we solve probability of x less than 1 and y less than 3 as integral over x is equal to 0 to 1, integral over y is equal to 2 to 3, 1 by 8 into 6 minus x minus y dy dx, which is equal to 1 by 8 into integral over x is equal to 0 to 1, 6y minus xy minus y square by 2 in the limits 2 to 8 dx, which is equal to 1 by 8 integral over x is equal to 0 to 1, 6 minus 6x, which is equal to 1 by 8 into 6x minus 6x square divided by 2 in the limits 0 to 1, which is equal to 3 by 8. Hence, probability of x less than 1 and y less than 3 is equal to 3 by 8. Next, we shall find the probability of x plus y less than 3. As x plus y should be less than 3, it could be considered as y is less than 3 minus x. Hence, the limit of the integral are x is equal to 0 to 1 and y is equal to 2 to 3 minus x. Then, probability of x plus y less than 3 is equal to integral over x is equal to 0 to 1, integral over y is equal to 2 to 3 minus x f of x comma y dx dy, which is equal to integral over x is equal to 0 to 1, integral over y is equal to 2 to 3 minus x 1 by 8 into 6 minus x minus y dx dy, which is equal to 1 by 8 integral 0 to 1 6y minus xy minus y square by 2 in the limits 2 to 3 minus x dx, which is equal to 1 by 8 integral 0 to 1 x square by 2 minus 4x plus 7 by 2 dx, which is equal to 1 by 8 x cube by 6 minus 4 into x square by 2 plus 7 by 2 x in the limits 0 to 1, which is equal to 1 by 8 into 1 by 6 minus 4 by 2 plus 7 by 2, which is equal to 10 by 48, which is equal to 5 by 24. Suppose that two-dimensional continuous random variable x comma y be given by f of x comma y is equal to 6x square y defined in the range 0 less than x less than 1, 0 less than y less than 1, 0 otherwise. Then verify whether the function is a PDF. Probability of 0 less than x less than 3 by 4, 1 by 3 less than y less than 2. Probability of x plus y less than 1. Probability of x is greater than y. For any function to be a PDF, f of x comma y should be greater than 0 and the integral of the function over the range of x comma y should be equal to 1. As both these conditions are satisfied by the given function is a PDF. Now, probability of 0 less than x less than 3 by 4, 1 by 3 less than y less than 2 is equal to integral 0 to 3 by 4 integral 1 by 3 to 1 6x square y dx dy plus integral 0 to 3 by 4 integral 1 to 2 0 dx dy. On solving and simplifying, this is equal to 3 by 8. Then probability of x plus y less than 1 is equal to integral 0 to 1 integral 0 to 1 minus x 6x square y dx dy. On solving and simplifying, we have the value as 1 by 10. The probability of x greater than y is equal to integral over x 0 to 1 integral over y 0 to x 6x square y dx dy. On simplification, we have the value as 3 by 5. The working part is considered as an activity. Now, we shall look into the application of bivariate continuous random variables in economics. Production functions. In production theory, bivariate continuous random variables are used to model the relationship between inputs and outputs in the production process. This allows economists to estimate the efficiency of different production technologies and to identify the factors that contribute to changes in output. Consumer behavior. Bivariate continuous random variables are used to model the relationship between income and consumption. This allows economists to estimate the income elasticity of demand and to identify the factors that affect consumer behavior. Asset pricing. In finance, bivariate continuous random variables are used to model the relationship between stock returns and macroeconomic variables such as interest rate, inflation and GDP. This allows the economist to estimate the risk and expected return of different investments and to identify the factors that affect asset prices. International trade. Bivariate continuous random variables are used to model the relationship between exchange rates and trade flows. This allows economists to estimate the effects of exchange rate movements on international trade and to identify the factors that affect exchange rates. Labor economics. Bivariate continuous random variables are used to model the relationship between education and earnings. This allows economists to estimate the returns to education and to identify the factors that affect labor market outcomes. Summarization. In this module, we have understood the concept of a continuous bivariate random variable. What is the probability density function of a bivariate random variable, its distribution function, and then solved some problems on these concepts. Finally, tried to understand the applications of the bivariate continuous distribution in various divisions of economics. Thank you.